Welcome to another unit in business mathematics. This time I'm going to talk about how we can calculate eigenvalues and, eigenvectors of any given matrix. Let's consider the exercises here. That's simply, as I said the objective already, calculate all eigenvalues and eigenvectors of the following matrices. Here we have actually 3 examples where I want to calculate eigenvectors and eigenvalues of. And I would say let's work through them, A, B, and then C. And if we start with part A, first off we have this 2 times 2 matrix. And if you recall the other examples, they were all quadratic. That's due to the fact that we can only calculate eigenvalues and eigenvectors for quadratic matrices. So that's one of the requirements. Well, once we have this matrix, what we actually do here in the first step is calculate the so-called characteristic polynomial. Characteristic polynomial means we take the matrix we have, calculate its determinant. But first, for each element on the diagonal, so here the 2 and the 5, we subtract a lambda. So we always go 2 minus lambda and 5 minus lambda. Now we calculate the determinant. Determinant in this case was this value times that value minus this value times that value, giving us here this expression. Well, here we have 0 times 3, so we can leave this, resulting only in this result. And that's actually pretty neat from its formulation, because this already tells us that our first null is 2 and our second null is 5. And that's actually what we need in the next step. We need the nulls of this characteristic polynomial, because the nulls of the characteristic polynomial, here 2 and 5, that's our eigenvalues. So to get the eigenvalues, get the characteristic polynomial, then get its nulls. So the first step in this example is already done. So we have the eigenvalues, and as each of the eigenvalues occurs only once, we can say that each of them has a so-called algebraic value or algebraic frequency of 1. We will go back to this term later in part C, so just recall here we call this algebraic frequency if it tells us how often certain eigenvalue is a null of the characteristic polynomial. If it's just once, has frequency 1. If it's 2, twice, it would have frequency 2, and so forth. And well, with this in the back of our minds, let's continue with the eigenvectors. And here we do this for each of the eigenvalues separately. So we start with the first eigenvalue of 2. So here we get the eigenvector for the eigenvalue 2. And we do this by taking the matrix and from the diagonals where before we subtracted lambda, for lambda instead now we use this eigenvalue. We do this. And then we actually solve the linear system of equations where on the right side we have zeros. So here I just directly used the, boiled down simplified version of this linear system of equations. But it basically reads as this matrix times a vector x, y equal to this, equal to 0, 0. Now we solve this linear system of equations. So first off, 2 minus 2 gives 2, 5 minus 2 gives 3. Well, we can simplify this a little bit so that it reads 1, 1 here. However, what we see, this system has one row which only contains zeros. So this has an infinite number of solutions. Actually, the number of rows where there are only zeros tells us how many eigenvectors we will actually find. So here we have one row with only zeros, so we will find exactly one eigenvector. Okay, so how to find this? Well, let's write down the solution to this system of equation. So for this we note the rows where there are any expressions. So the second row here reads as x plus y equals to 0. And then we write one of the variables in relation to the other. So here we write x equal to minus y. Then we select one of the variables as arbitrary. Well, here it makes sense that if we write x in relation to y, we set y to be arbitrary. So this results then from the first row, which is only zeros, that y, which is selected arbitrary, is also equal to y. Well, it obviously is equal to itself. Meaning, we have here the definition of our solution. Our solution vector is actually minus y plus y. So if we take this solution vector, we can simply factor out the y, write the y in front of this vector, leaving us here with minus 1 plus 1. This vector here, the minus 1 plus 1, that's actually the eigenvector we were looking for the eigenvalue 2. Well, we did this for 2, so here, this is our eigenvector value, this is the corresponding eigenvector. Now we can do the same thing for the other eigenvalue, which was 5. So here we have the eigenvalue 5. So we do the same thing over again. Instead of going minus 2, for lambda now we use 5, but the rest is the same. Solve linear system of equations, which is equal to 0, giving us here first after simplification minus 3, 0, 0. Here we can see that we can add the first to the second row, giving us here one row with zeros, meaning we have one eigenvector. And then we can simplify the first row by dividing by minus 3, giving us 1, 0, 0. So if we take the non-zero rows, so the first one, write them down, it just states x is equal to 0. So of the other variables, we select one as arbitrary. So here, this is then again the y. We can use this to write down our solution, or solution vector. So we know x is equal to 0 and y is y. Then again, we pull the y in front of the vector, giving us here as this direction 0, 1. So the 0, 1 is the wanted eigenvector for the eigenvalue 5. So this is the eigenvector for this eigenvalue. Well, with this, we concluded the first part. We found the eigenvalues. Then based on the eigenvalues, for each of the eigenvalues, we calculated the corresponding eigenvectors. So let's continue with a slightly more sophisticated, let's say, problem. That's a part B, because here we have a 3 times 3 matrix. However, the procedure is the same. First off, we calculate the characteristic polynomial by subtracting lambda from each of the diagonal elements and calculating the determinant of this matrix. To easily get our result here, we can use the rule for determinants. So we select a row or a column with as many zeros as possible. So let's go here with second column. Wherever there's a 0, we can skip this. So we only have 2 minus lambda, so we use this. Then we need a sign for this. So we start here with plus, minus, plus. So it's always changing, always starting in the upper left with a plus, plus, minus, plus, having here plus. And then we need the determinant of the reduced matrix. Reduced means this is in the second row and second column. So we eliminate second row and second column. Those are eliminated, we're only left with these parts, this, and that. And then we can again, for the rest here, use the rule we know for 2 times 2 determinants. So this times this minus this times that, making it look like this. The advantage is, here I already see that my first eigenvalue is 2. However, for the part in here, even if I simplify this, I get this expression. So I would have to calculate at this point the nulls of this expression here. So for this, I can ideally use the PQ formula. And if I do this, this results in 2 additional nulls, 6 and -1. So in this regard, I get actually 3 eigenvalues, 2, 6 and -1. And we're going to work through all 3 of them and get for each of those 3 the corresponding eigenvector. So we start with the first eigenvalue with 2. As before, we insert this here into our matrix, where before we had the lambda. This simplified into this linear system of equations. We can then, to make this one step easier, simply subtract the first row from the third, giving us here this expression, and then we divide the third by 6. If we write the first and the third row, because they are the only ones with any input, down, we get those 2. From the third we know x is 0. Well, the first one reads as -x plus 2z equal to 0. Or, if we rewrite this and solve for z, we get z equal to 1/2 x. Well, combined with the third row, where it says that x is equal to 0, we also get that z is equal to 0. So we have 2 variables which are defined. We have 1 row with only zeros, meaning we have to select one arbitrary variable. This is then, well, the only one left, which is y. Then we can write down the solution vector again. X was 0, z was 0, and y was y. We write the y again in front of the vector, giving us here as a vector 0, 1, 0. And this is the eigenvector for our eigenvalue 2. Okay, so far so good. So that's the first eigenvector. Let's continue with the second eigenvalue and its eigenvector, which here was 6. So again, we insert 6 into this matrix and therefore into the system of equations. This results in that we see the second row we can divide by -4, and the first and third are actually the same, but with a factor of -1. So I can actually add the first to the third, which would get rid of this, and we would have 1 row with only zeros. So if I write them down again, first and second row, the only ones which are not only containing zeros, I have here from the second one, y is 0, and the first one, -5x plus 2z equal to 0. In this case, I could write this, for example, in relation or independence of x. So z would be equal to 2.5x, and well, obviously, x is equal to x. Because I would have to select one variable, which remains flexible, and it's a suitable choice to go with x here. So the solution would add up to x being equal to x, y being equal to 0, and z being equal to 2.5x. Then we pull the x in front of this. We get as a vector here 1, 0, 2.5. So this 1, 0, 2.5 is the wanted eigenvector to the eigenvalue 6. Okay, so far so good. That's 2 of the 3 eigenvalues done. We can continue with the third and final eigenvalue, which was -1. So again, insert here for lambda -1. As this was minus lambda, we get -1, so +1. And the system of equations look like this. Now we see that the third row is again a multiple of the first. So we can subtract this, giving us again here one row with only zeros. Then we also divide the first row by 2 and the second row by 3, leaving us with this result. And if I again write this down, I see again, second row means y is 0. First one is x, 1x plus 1z equal to 0. Or if we again write this in relation to x, z is equal to -x. One row of zeros means one variable I have to select to be equal to itself, which here is a good choice, being x. So this then gives our solution vector, which here is x is equal to x, y is equal to 0, and z is equal to -x. We pull the x in front of this and get as a result 1, 0, 1, -1. So the 1, 0, -1 is then the wanted eigenvector to the eigenvalue -1. And this then concludes as well exercise part B. We can continue with part C, this matrix here. So similar to before, we start with the characteristic polynomial by subtracting from the diagonal elements minus lambda and calculating the determinant. Similar to before, what we do here, we select one column or row with as many zeros as possible. And in this case, I go again here with the first column. So I have 1 minus lambda here. Then the next one is 1. The signs for them are plus here. Next one is minus here. And then I would have plus 0. Well, it's 0, so I can skip this. And for the first one, for this one, I delete first row, first column, because that's where this part is situated, leaving me with this part down here, which is just this reduced matrix. And for the 1, this is in the first column, second row. I delete second row, first column, leaving me with 1, 2, 1, 1 minus lambda, which is this part here. For those two determinants, I simply used the determinant function for 2 times 2 matrices. So this times this minus this times this. And here, this times this minus this times this. Which in the end looks like this. We can simplify this by calculating all the different expressions, summarize it, and we get this as a result. Minus lambda to the power of 3 plus 3 times lambda squared. And here we can actually then factor out minus lambda squared. We have this. Because this tells us that 0 already is a null. Because if we insert 0 due to the lambda squared, this will be 0. So we have a double null at 0 because it's squared. And we have a single null at 3. So we have 3 nulls, a double null at 0 because it's lambda squared, and 1 because it's only lambda minus 3 in parentheses to the power of 1. So if I return to the comment I made earlier about algebraic frequency, here the eigenvalue 0, because well we said the nulls are the eigenvalues, the eigenvalue 0 has algebraic frequency of 2. The eigenvalue of 3 only has algebraic frequency of 1. With this in mind, we can then continue calculating eigenvectors. And there, we can also keep in mind that the number of eigenvectors to any eigenvalue is limited by its algebraic frequency. So if here we have a frequency of 2, we could get 2 eigenvectors for this eigenvalue. We not necessarily have to get 2, we could also get 1, because at least you will get 1, but you could also get 2. Here, we can only get exactly 1. So let's test this for the double eigenvalue 0. So for lambda, we insert 0, giving us this system of equations, which looks like this. And if we look critically here, we can see from the second row, we can subtract the first, giving us 1, 0 row. But if we try to simplify this even more, we can only subtract the third from the first, making it look like this. Well, that's similar to parts of what we had in B, because if we just take the first one, this reads as x plus z equal to 0, or x is equal to minus z. The third row is y plus z equal to 0. So here we can also write the y, independence of the z, also as minus z. Then we need to select one additional variable freely, because we only have one row with only zeros here. So let's select z freely. Then this directly gives us our solution to the system of equations, which here is minus z, z. And if we pull the z in front of the vector, we have z times minus 1, 1, which is the wanted eigenvector to this eigenvalue. So here we see, as I mentioned earlier, this has algebraic frequency of 2. So it could have 2 eigenvectors, but it only has 1 eigenvector. And here we can differentiate between the algebraic and the so-called geometric frequency. Geometric in this context means how many eigenvectors can I find? It will always be 1, but it is also smaller or equal to the size of the algebraic frequency, so the number one eigenvalue is present. So here it's actually a case where the geometric frequency is smaller than the algebraic one. And well, this still leaves one case open because this was only one eigenvalue. We still have to go for the second, which was the 3. So if we insert 3 for lambda, we get this system of equations, which then reduces to this part. Well, what can we do here? Well, first idea would be get rid of those 2's here. So add the third to the first and the second row, giving us this part here. And then, if we look closely, we see that the first row is a multiple of the second row. So if we add the second twice to the first, this will result in this part here. Now we cannot simplify this anymore. We have one row with only zeros, meaning we get one eigenvector. If we write down the second row, we get x minus y, or x equal to y. If we write down the third one, we get y minus z equal to 0. If we solve this for z, or rather also write this independence of y, we get that z is equal to 1/2 y. Well, we need to again select one variable arbitrarily. This would then be a good choice to go with y. Putting this together yields as a final result x equal to y equal to y, z equal to 1/2 y. Or, if we pull the y in front, 1, 1, 1/2. The 1, 1, 1/2 is the eigenvector we wanted for our eigenvalue of 3. So this then also concludes this part C. In this case, we found out we have 2 eigenvalues, one with an algebraic frequency of 2, which however only has a geometric frequency of 1, and the third one, or the second eigenvalue, which has an algebraic and a geometric frequency of 1, because only one eigenvalue, only one eigenvector. Well, that's then it about this exercise, so I hope you enjoyed it, and I say goodbye and see you next time.